In this video, we'll be going over Beer's law and how to get absorbance from a calibration curve. So on this first slide, we're going to go over how a spectrophotometer wavelength setting, how to set the wavelength, which would correspond to what color substance you're putting in the spectrophotometer machine. So in the lab we're doing, we'll be analyzing crystal violet. This is a little bit later. And it's a violet color, as implied by the name. So here's our spectrophotometer machine, and then we're going to take our crystal violet and we're going to put it into the machine. And the crystal violet has a knob, and this knob allows you to change the wavelength. Wavelength is given by the Greek letter lambda, and so we need to know what wavelength of light to shine through the crystal violet solution. So this is gonna, do we want the wavelength to go like that? Do we want the wavelength to go like that, etc.? So it depends on what color it is. And what color it is depends on the pigment. So this is actual dye that makes this right here is the actual dye that makes this purple. So we need to adjust the knob to be absorbed by this molecule. So the colors that the color that violet transmits is this wavelength, 400 to 450 nanometers. That's the color it transmits. So that's not the color it absorbs. That's the wavelength that it's giving off. This is 450. Okay, and this goes into our eye, and then we perceive it as being violet. So what color is it absorbing? The dominant colors that it absorbs are actually complementary. So we need this. This is what we need to set the machine at is 460 to 600. There's another lab where we take colored food dyes, such as like blue or red, like fruit punch and like blue Gatorade, and the blue one is obviously going to transmit this color. So on that experiment, we would set the machine at 600 to 640, around that wavelength here on the knob. Okay, so for when we do this crystal violet one, though, it's going to be around here, the wavelength that we're going to be setting it at. That's going to be the optimal wavelength. All right, so how do we this will, okay, so the light will go through the purple substance and a full beam of light, but only some of it will go through. Okay, so only some of it is actually going to go through on the other side. So the remaining amount is what got absorbed, and the machine is going to show us the absorbance right here. It's going to give us a absorbance reading. Okay, and we need a way to convert this. So we need to get this to concentration or molarity. Okay, as you might expect, the amount of light that gets through is directly related to how concentrated the solution is. So if it's really heavily purple, it's going to absorb more light. So when you get a higher concentration, it's going to absorb more photons of whatever wavelength we set it at. So this actually will, and this is on the next slide, this is actually Beer's law. The absorbance is equal to a number called A times a number called B times a number called C. And so on the next slide, I'm going to define what those letters are. So this is Beer's law. So what this is showing is the amount of light that got through. So this right here is the initial light, and this is the transmitted light after some of it has been absorbed. Okay, this is a little bit more detail on what we need to go over, but the absorbance here is unitless, and it's the amount of initial light divided by the amount that that actually got through. So your numbers can be greater than 1 here for absorbance. So it's not like a fraction of light that got through. It's actually the amount initially divided by the amount transmitted. An important point as far as the math that we're going to be doing is that this number is unitless, the absorbance. This letter called A is this right here is called the extinction coefficient. Extinction coefficient. And this letter B right here is the cuvette length. So back on the previous slide, that was this which I had colored purple on the previous slide. So the container that it's in is called a cuvette. It's a little rectangular container. It's almost always 1 centimeter. I have seen when it's not, so don't just assume it is, but usually it is. It's 1 centimeter. And C is the concentration of the sample. So we're going to do this example problem. So this is called a calibration curve. You're basically trying to calibration curve. What you're trying to do is establish this equation. You're trying to establish Beer's law and find the connection here so that you could get the slope. So this is actually, so A would be like y, and A times B is actually the slope, and C is x. So this is y equals mx. So this actually will give you a straight line. And what we're trying to figure out is m by experiment, so that you could figure out a new question, such as once you find out the relationship and the slope, then you could figure out like some absorbance. So what if I put a unknown sample in and it's super concentrated, it's really dark, and the absorbance reads like 3.90. Okay, what would this be? So if we come up with a relationship and we get the slope of this line, then we could figure out what that point would be. So some point where this would be the absorbance and this is the concentration. So say we want to know like some line or some new data point that's way off the graph, like 3.90, and we want to know what concentration that is. Well, if we have the slope of that line, we can answer that question. So that's the purpose of creating a calibration curve. So what you do is you do this by, if you notice that these concentrations from here to here are halved each time when you go up like this. So this is called when you get more and more diluted like that, it's called a serial dilution. And it's a really common lab practice in creating a calibration curve. Okay, I jumped to a slide on accident. Okay, so let's try to answer this question. So this data was collected. You get a sample, like let's say you start with really dark purple, right? And then that's your concentration, and you'll get some absorbance. So you take this and you cut it in half, meaning you take half of it. So you take half of that and then you add half water, then you'll get this concentration, and then you'll get this absorbance. And then you take that and you cut that in half, then you'll get this concentration and this absorbance, and so on and so on. Okay, and then you'll get those. That's called a serial dilution, and the purpose of that is to get this calibration curve. Okay, and then you plot the points, or using a graphing utility, Excel or your calculator, you can get this. I had a graph shows up, it's taking up too much space on my slide. So I'm just going to answer a little mini quick practice question. So if I plug this data in, I'm going to go. I'm going to open up my calculator.
Okay, and I'm going to go to stat, and it looks like I probably have something in there from before, so I'm going to clear this out. Clear that out. Okay, the L1 default is X, and I want the concentration to go on the X-axis, so I'm going to go 0, and then 1.2, 2.4, then 4.8, to the -3, then 9.6. These are the concentrations times 10 to the negative third. Then 1.9 to the negative second. Okay, and now I'm going to add in, for my y data, I'm going to put the absorbance. I'll put 0, 0.15, then 0.31, then 0.70, 1.25, and 2.62. Okay, so now I'm going to go to, I'm going to make sure
my plot is turned on. So go to stat plot, make sure it's on. Make sure I'm not graphing anything else. So now I'm going to hit graph. So I think I'm really zoomed in. So I'm gonna press zoom, and I'm gonna choose this where it says zoom stat. So I'm gonna hit 9 right here, and there's my line. So if I go to stat and calc, because I want the slope of this line, I'm gonna go down here to number 4. Hit enter and calculate this slope of that line. And I get my slope as 137. If you look at the data over here, I have my absorbance are only to 2 sig figs. So, and my concentrations are only 2 sig figs. So my slope is, I'm going to only use 2 sig figs. So I'm going to round this to 140. Okay, so using the graphing utility, I got A equals A times B. So A is my slope. This is M. B, I mistakenly, because it's almost always 1, I made a small mistake there. So A is actually slope. B is the cuvette length. Okay. So my M in that case was 140. Okay, times 1 centimeter times C, and that equals the absorbance. Okay, so I'm going to ask a question here. So I'm going to ask, so what, an unknown substance or it's actually known, it would be, let's see. Usually these are known, sorry. And then, so you have a substance and it has a absorbance of 1.84. Okay, what's the concentration? Okay, and it could be unknown. Doesn't really matter. Okay, so to solve for concentration, now that you have the calibration curve, you can answer that question. So it's some point much later. Okay, I'm having some problems here. So you would get your absorbance divided by 140, and this would have to be inverse molarity, the extinction coefficient, times 1 centimeter. Actually, it's inverse molarity times inverse centimeters cubed times, that's it. Okay, and so the answer to this would be 1.84 divided by 140, and it would be 0.0, having a lot of problems here, so 0.013 molar for the concentration. Okay, so there's some reasons why your graph might not be straight. So you're supposed to really wipe down the cuvette with these things called Kim wipes. So that could increase the absorbance and make your data higher than it's supposed to be. So that can mess up the slope that way. The material undergoes a chemical change when exposed to the actual wavelength. And the material involved might be doing equilibrium, so it might be dependent on equilibria. So it might actually be reacting with itself and making more or less of something. So those are reasons why it might not be exactly straight. Okay, so here's the your turn question. Okay, and so an experiment was conducted. This is a calibration curve data was obtained. And then see if you could answer this question. So you have then a new sample was used. So using your calibration curve data, see if you could figure out the concentration when the absorbance is 0.539. Okay, so that's the end of our video. Sorry for all the skipping around. I was having some technical problems.